My name is John Cesario. I'm here with my coworker Ryan Lowe, and we're going to talk about Neo4J and how we use it at Square. Ryan and I both work on the platform engineering team at Square, where we manage thousands of MySQL, Redis, a little bit of Neo4j, and a slew of other data stores. We have 50 minutes today. We're going to try and keep the talk between 35 and 40 minutes, and we'll try and give you guys 10 or 15 minutes at the end for questions. If you do have questions, feel free to raise your hand, and I'll happily stop, and we can try and get that resolved. Neo4j is a newcomer at Square. We've been flirting with it on and off for a couple of years now, and it's only really been in the past year that we started to feel it added enough value to warrant putting engineering resources on it. The purpose of today's talk is not so much to deep dive into how we use it at Square, because we don't feel like we've really gotten the full potential of it yet. Rather, we want to talk about the things that surprised us and how we kind of worked around them, and only talk about a little bit about a couple of use cases that we have it for. Is anybody here from Neo4j? Okay, good, great, because the TLDR, we like it, it's really cool. It's got a long way to go. It's got a lot of sharp edges around operational tasks, and it's nearly impossible to deploy it to the same type of level that you would expect from a normal database without paying the license. A lot of the features are behind the paywall. And I hope you're all here because you're interested in Neo4j, or Bill just needs internet. So we probably don't need to spend a lot of time talking about graph databases, but we'll give a quick overview. In my mind, the idea that really sums up the reason that we want to talk about graph databases is that in traditional databases, we're interested in individual data elements. And in graph databases, we're more interested in the relationship between these elements. These diagrams are from the Octo blog on graph databases, and they model the exact same thing. You notice the graph on the right, the graph model is far cleaner. And so graph databases gained extraordinary popularity due to like social networks like Facebook, Twitter, or LinkedIn, and then exploded when people started doing things like fraud detection and internal relationship analytics. The concept of graph databases was born because calculating relationships in a relational system is not very efficient. To use Facebook as an example, it's really easy to see like whether or not person A and person B are friends. And it's kind of easy to see who's friends of these people. But if you go beyond that type of graph depth, you get terrible performance characteristics in a typical relational model, and it can make it practically unusable. Graph databases focus solely on relationships between items. Connections between items are mostly pre-computed and stored so that access to them is in constant time, even when you have millions and millions of nodes or vertexes. Graph databases excel at managing highly connected data and are designed to be accessed via complex queries. It should be obvious based on the description that I just gave that graph databases are designed primarily for read usage. The vast majority of use cases you find are going to end up accessing data that was bulk loaded via ETLs or nightly jobs. And if you've seen any Neo4j webinars or talks in the past, you've probably seen this exact slide. These are the prototypical use cases for graph databases that emphasize relationships. And so first up, we're going to talk about real-time recommendations. This is probably the example you guys see the most, besides Facebook, obviously. And this comes from Amazon. So every time you make a purchase, every item you view and every search string you enter is put into the database. So they can build relationships like Ryan purchased X and viewed Y, and then he searched for Z. John purchased X, viewed Y, searched for Z, and then purchased item Q. And therefore, we should recommend item Q to Ryan because he'll probably buy it. The same things happen with LinkedIn recommendations. We can see that Ryan is connected to some people and viewed the other people, and people who fit that pattern often end up connecting with this other person. So let's recommend this other person to Ryan. Or a specific recruiter has viewed Ryan's profile 100 times in the last few days, and clearly there exists some relationship between them. So let's spam Ryan's inbox with recruiter spam. This use case is incredibly powerful from a financial perspective. How often have you gone to an Amazon page and made a decision based on people who were searching for this bought this, right? So that's kind of what we're trying to do here. We're trying to figure out how to encourage people to make significantly more purchases based on data we have from their common relationships. And I know I've fallen for this more than a few times, right? We do something very similar to this within Square. The graph shows related product usage across a tiny subsection of merchants. You don't really need to read the text, don't worry about it. We use Neo4j to track what products customers use and how they might relate to other customers. We then apply machine learning to the Neo4j graph and use the models it generates to better predict which products we should cross-sell to any given customer. A practical example of this is, for example, if you own a hair salon, we know that in addition to taking credit cards, you probably want appointments as well. And this allows us to drive cross-selling in a very appropriate and non-invasive way. And next use case, we talk about master data management. Master data management is typically used for organizational hierarchies. John manages Ryan, Ryan manages Daniel, and all three of them work on the platform engineering team at Square. Pretty simple structure, right? And it's great to see these kind of official, unambiguous structures in an organization, but it's also incredibly useful to find the unofficial structure. So in addition to the formal reporting structure, you can develop relationships between people based on projects, such as John worked with Mary on project X, and that would be considered an unofficial relationship. But doing things like this, you can highlight individuals or teams who may be incredibly important to many projects, but that they may not have an official involvement with. Everybody has people in their organizations who's like the unofficial, like, master of everything that gets brought into various projects, and this can help highlight those people. Another really cool use case is an extension of this. You can do data mining on your internal email or chat servers, and you can see who is communicating with whom and to what extent. This surfaces individuals who exert a lot of informal influence and leadership that people unofficially rely on. And it can surface people it can also surface people who are big receivers of requests. They have a lot of inbound chat, they have a lot of inbound email, but perhaps they don't send a lot out to the same people, and that'll let you know that maybe this person needs to have their workload examined. For us at Square, fraud detection is the thing that led us to Neo4J. We originally used MySQL for fraud detection, and it served us well, but it's certainly not the only tool we have anymore. When we were first founded, our first priority was, of course, to start taking credit card payments. But fraud detection was a big thing from day one. Of course, it's changed significantly. There was a time when a single indicator was enough to detect the vast majority of fraud on Square's network. Can anyone guess what the biggest indicator of fraud was? Anybody? Yeah? No, nothing? Florida, right? That was it. Yeah, right. It's always Florida. So that was really the only metric that we really used. But today, obviously, it's much different. Fraudsters have gotten organized into sophisticated groups that use stolen identities and hijack devices. And both buyer fraud and seller fraud have gotten orders of magnitude more complicated as well. We track thousands of data points and establish relationships that identify fraud rings. For obvious reasons, we're not going to get into specifics, but just suffice to say, we don't just track Florida anymore. This graph is a tiny, tiny portion of what we call our connected entities graph. It shows several merchant tokens and how they are connected to each other via relationships. Our risk team uses Neo4j to do fraud detection and prevention because it's a great supplement to our other tools. Fraud rings will often use shared assets. So they'll use the same reader, the same phone. They may even share the same SSN or bank accounts because many rings end up using the same stolen identities. Using graph models, we can track and catch fraudsters and freeze all the assets associated with a fraud cluster. This graph also allows us to monitor new users who are tied to fraud rings by some shared asset. For example, a new user may have been given an SSN that was associated with a fraud ring that was already identified in the past. And this allows us to kind of short circuit the process and get in front of fraud. Graph-based search allows multifaceted search through large data sets that provide an additional dimension to regular searching. The reason graph-based search is powerful is evident when we contrast it with the data structures in relational search. In relational search, the underlying structure is most commonly a tree of some kind, which only ever has a single edge to its parent vertex. While this is great for seeking to a specific piece of information in the tree, it is inefficient when used to describe graph models. At its core, graph relationships may be modeling n relationship to the parent, and so the parent is not totally evident. So we have to have different algorithms in order to quickly discover various subtrees based on a specific vertex. Graph search allows you to walk that graph and, for example, find all users that are connected to John that have also purchased Y. So you can see there's like many, many relationships between that statement. And the nice thing about graph structures is that this can be done in near constant time. Another super obvious example of graph models would be network and IT operations. I'm sure everybody here has used dependencies in Nagios, right? So this computer is plugged into a bunch of PDUs and also this switch, and these switches are further dependent on routers. The power of using graph-based databases here rather than hierarchical or relational databases is that it allows arbitrary structures to be modeled, which is really needed for modern networks. It's also really good at expressing complex layers. It's not just physical entities, but also logical things like services, clusters, and inter-service dependencies, and we'll see examples of that later. This can really help in root cause analysis and post-mortem documentation. There are a number of monitoring vendors that include this capability in their products, and it can be super useful when the size and complexity of your network has grown past the point where a single individual can understand it. Using graphs to model identity and access management is super useful when there are multiple layers of security and complicated access schemes. Simple role-based access control isn't enough for organizations like banks or the NSA, where access needs to be managed at various project, privacy, job titles, and classification levels, so each individual has many different layers of access. Graphs can be useful in modeling, for example, the limits on the user accounts when you need to go to a dual signature type of operation, and on the fly access changes based on organizational roles. Who has access to what and when is often a non-hierarchical structure. It's rich, and it has a rich connection of connected data, and this is where graph databases thrive. State machines are my favorite use case at Square. We made a graph of the payment-related screens in our Android application. So we wrote a state machine to keep track of payment screen transitions and payment events on our mobile Android app. By monitoring a Kafka screen, we are able to track which screens a user visits in near real time. Screens are accessed via either triggered transitions or by payment events, card taps, dips, swipes, etc. What this does is it helps us visualize the complexity of our application. We then realized the state graph can be applied in other ways. We populated a graph with all screen transitions through all platforms. What this does is it helps us support our customers when they call with issues, as we can actually trace through their steps on the graph up to the exact moment when they file a support request. We can then apply machine learning to the patterns of all users and predict when a user will need help based on previous actions from other graphs. Another use of this state machine is mapping our microservice architecture. We have several ways to get an overview of how all the services talk to each other, but historically we have had no way to query this data. And now we can run queries like find all services that would go down if service X goes down. And this is really, really useful for impact analysis. And this concludes the introduction to Neo4J, and I'm going to turn it over to Ryan for some words about Java.
Thanks, John. So the structure of this talk actually changed really significantly about a month ago. John and I got an invite for one of our risk teams, and usually when the risk team invites you somewhere, you're going to do some big data, you're going to do some complex analysis, it's going to be fun. But in this case, we walked into the meeting and they said, Ryan, John, we have a case of the Javas. The first thing that you're going to notice about Neo4J is that it's written in Java, and unless you have experience administering other Java services, you're going to have a bad time. So I really apologize in advance for the next 15 minutes, but your future selves are going to look back on this gratefully. We'll talk about things like Java threads and thread states, what the garbage collector is doing, things like that. And these are some of the things that we believe are the most important for like outage situations and impact analysis. So let's start first with a very brief overview of the Java virtual machine. For those of us who aren't familiar with running the JVM in production, most languages compile code into machine code that you run directly on the machine. In Java, you don't do that. You don't have machine code. Java gets compiled to bytecode instead. And bytecode is a nice little layer of indirection that gets run by the JVM. It's not run on the machine directly. And this is actually kind of cool. This layer of indirection gives us a chance to inspect a live running system, add breakpoints in the middle of it, and all sorts of things like inspect memory heaps and stuff far more easily than you can do with, say, a binary in C or something. And there are many implementations of the JVM. The JVM is actually a simple spec. The most popular, of course, is Sun's original reference implementation, and Sun did something pretty cool prior to their acquisition by Oracle. They open sourced their implementation as the OpenJDK. So the OpenJDK shares a lot of DNA with the Oracle JVM, but at this point it's on its separate path. There are IBM and a few others have their own JVMs, but we're mostly assuming that everybody here is running the Oracle JVM because that's the most popular, but the principles here apply to most. A quick side note that's worth mentioning is the JVM is actually language agnostic. You can compile JavaScript, Ruby, Python, Scala to bytecode that will run on the JVM. So now then we know what the JVM is. Let's talk about threading. The JVM is a multi-threaded environment, and JVM threads are backed by system threads. But on older versions of Linux, the JVM could use something called green threads, which sort of emulate threads in a multi-threaded environment. So it's important to use a modern OS for Neo4j. There are two different types of threads. The JVM has its own set of housekeeping threads for things like garbage collection, finalizers, and stuff like that. And then you have application threads. So coming from the MySQL world, there's typically not a lot of overhead like this, except for like purge threads and things like that. So your Neo4j instance will not only need fast enough CPUs to make the execution of a single-threaded query performant, but also enough CPUs so that your JVM internal threads don't compete for resources with your application threads. So let's look at a thread dump. That's what you've got there on the right. There's a ton of information there. You've got a stack there to see what the thread is doing. The top one there is your main thread. That's the thread that starts when you run a Java program from the command line. It has a main method, goes through a bunch of stuff, and you can see that it's currently waiting for something to happen. In this particular case, it's created a bunch of thread pools to listen for inbound requests, and the main thread is just waiting for it to finish and shut down. You can see a couple of JVM threads as well, finalizers, signals dispatchers, and things like that. And there's an application thread. You can see it's formed a thread pool. It's waiting for something interesting to happen. There's quite a lot of good information here. And you've got thread IDs, which are super useful for debugging. And this is a very super small snippet. A full thread dump is typically going to have hundreds of threads. They're big. They're complicated to read, but you can learn a lot from it. And it's important to know things that you can get from this, like what state a thread is in, what it's waiting on, what references it's holding, things like that. And I've shamelessly copied this from the thread.state Java doc. I'm not going to read it, but these are the states that a thread can be in. There are only 6 different states, and they can only be in a single state at a given time. It's really important to know exactly what states mean. It's like, you know, the general thread states in MySQL. You should know all of them. So that's enough about threads. Let's talk about memory. The JVM is a complex beast. Memory management and physical layout can change drastically between major versions, and this actually reflects Java 8, which is the version that Neo4j mentions in their docs. So when you start it up, it allocates a big chunk of memory for you to work in, and that's both for your application and the JVM and some other stuff as well. And we'll talk in a minute about how you can cap the amount of space that's used by the heap, but the heap isn't everything. It allocates space outside the JVM as well. We're not going to deep dive into this right now. We'll talk about the relevant bits in a couple of slides, but in general, you've got your heap, and this is where your application lives. And then you've got the method area. That essentially is the JVM itself. The JVM loads classes from class loaders and jar files, and this is where the class definitions live. And then you've got your native area where your JVM talks to system libraries, and Neo4j can actually allocate things off heap as well, and that's kind of interesting sometimes. A couple things, actually this slide is a little bit wrong. In Java 8, the perm gen has gone away in favor of something called the metaspace. They serve almost the exact same purpose, but some slightly different things, like your constant pool isn't there anymore, it's back in the heap, things like that. So the Neo4j documentation recommends a heap size somewhere between 8 gigs and 16 gigs for normal operations, but depending on your data set and workload, it's not uncommon to see heaps up to 32 gigs. A quick side note, Java has something called compressed object pointers, which can save space, but they're not enabled above heaps of 32 gigs. So there's basically like a no-fly zone for heaps of between 32 and 64 gigs in modern systems. If you want a 64 gig heap or larger, you've got to change, make changes to your JVM environment, use the G1 garbage collector. But that'll become the default in Java 9. All right, so let's talk about garbage collection. Everybody know how garbage collection works? All right, I got 2.5. This is only a super high level intro to garbage collection, so everybody, whatever JVM you're using, whatever version of Java you're using, become super intimately familiar with your garbage collector. As somebody operating a database that's written in Java, this is the single most important thing that you want to know. Java garbage collection. And the reason being is that you can learn a lot about the health of a system by looking at it. You need to treat the system as a black box, right? Like we don't know Neo4j. You don't know specifically what it's doing at any given time, but you can tell potentially what's wrong with it by looking at the way that it's doing garbage collection. And this is also the area that people get things slightly wrong, it's slightly complicated, and a lot of people think about it as a kind of voodoo that they don't want to know about and they want it to manage itself, and it kind of does, but it's still one of the areas that you really need to understand if you're going to operate Neo4j. But of course, there are drawbacks to running in a virtual machine. As operators of Neo4j, this is where you're going to feel the pain. Garbage collected systems like the JVM can be memory and CPU intensive. Memory may not be reclaimed as quickly as you want. Things like background threads are dedicated to housekeeping tasks and the like, and there are pauses, right? GC pauses are what people refer to when they say we have a case of the Javas. Sometimes you have to stop and clean up your heap, and that can be very expensive. And of course, like I said, tuning it can be complicated. And it scares people away sometimes, but hopefully at the end of this talk, you won't be afraid of tuning your JVM and garbage collection for your Neo4j instance. So let's talk about the different phases of garbage collection. Before we proceed, the collector that I'm actually going to talk about is called CMS. Going back, there are different JVM vendors. Each one of them has their own garbage collector, and even within the Oracle Sun OpenJDK, there are a bunch of different garbage collectors as well. So I'm specifically going to talk about CMS, but a lot of the stuff is pretty general. There are different ways of collecting garbage in an allocated heap, right? The most populars are mark and copy, mark and sweep, and then mark, sweep, compaction. Marking and copying is going to be super simple. You have a chunk of memory, you've got a garbage collection thread that goes through it, marks which objects are in use, then it copies them to a new area and throws away the old space. It's a very simple algorithm to do garbage collection. It copies the object still in use to somewhere else, then you use that as your heap. Marking and sweeping, it's the diagram on the right. The pros and cons to each approach. Marking and copying is extremely fast. It's extremely simple. It's extremely simple to reason about, but it requires a ton of extra memory because you're effectively doubling the space. So you're copying the old data to the new data, to the new space, excuse me. Mark and sweep is pretty efficient, but you end up with a lot of fragmentation, which means if you have a big object that can't fit anywhere, it's a problem, right? So with Neo4j, if your workload is consistent such that you're always doing the same kind of query on roughly the same set of data with roughly the same size result set, it's probably going to work fine. But if you've got a mixed workload where you've got a lot of really small objects being allocated, a lot of small queries on small data sets with small results, and then sometimes you get large queries that operate against large data sets and have large results, you're going to have a bad time. And this is where we've felt the pain of tuning the JVM and the GC. It's on these systems that have really, really mixed workloads. Mark, sweep, compaction, it's a bit more CPU intensive. It's doing a bit more work, but at the end, you have a nicely compacted memory space. And most GC algorithms use a combination of these for different paths and different regions, and we'll talk about that in a bit. So, pauses. You can't have the application creating new stuff while you're trying to remove stuff, right? You end up with things getting out of sync. So there are a couple of states where the JVM needs to save point itself, which basically tells the application, or Neo4j in this case, stop doing any work. Then it comes through all the pointers, find out where everything is, and then it lets the application threads continue to do stuff. And in CMS, there are basically two real pauses. We call them stop the world pauses because the world stops, where you do an initial mark and then another one when you do a final remark. But usually, like the sweep and copy phases are cheap. They don't stop the application threads for very long. So let's talk about generations. Most garbage collectors in the JVM are what we call generational collectors. The whole concept of a generational collector is fairly simple, right? Not all objects live for the duration of the entire application. Some do, some do not. Some live for a very, very short period of time. In Neo4j, most objects that you create to answer a query get thrown away at the end of the query because they're not going to get used anymore. They're very, very short-lived. And that's the bulk of the stuff that you're going to do. Some objects survive a little bit longer, such as the things that survive for the duration of a session. And then, of course, there's objects that last even longer for the entire duration of the application, things that don't actually go away until you restart Neo4j. So as a result, you have different amount of garbage that lasts different amount of time. Now, if you put everything in one heap, that's going to be really inefficient because you're combing through everything and you don't have different sort of time frames, lifespans. So this is where generational collectors come in, where you actually break your heap into like a young generation and an old generation. Stuff that lives for a short period of time, lives in the young generation, and is really cheap to collect. They use different algorithms optimized for cheap, fast collections, and then you can comb through stuff later, go through the entire heap and inspect the older, longer-lived objects to see if they need to be collected. And that's generally the idea of generational garbage collection. And in CMS, again, because I'm mostly talking about CNS, You have the young generation and the tenure generation, or the old generation, and then the metaspace, which is actually outside the heap at this point. It's actually just class definitions from your class loaders, not generally Neo4j stuff. And that's all the stuff that doesn't get garbage collected. So young gen is split into Eden and survivors. We'll talk about what those are in a second and how they work. But in general, the idea is that Neo4j starts allocating objects, and these objects tend to start in the young generation. And as the young generation fills up, they get promoted to the old generation. Going into a bit more detail, the way these survivor spaces work is the young generation is typically a mark and copy, and that's the sort of algorithm that goes into the Eden space because it's very fast. In the old generation, you tend to do mark, sweep, and compaction. Survivor 1 and Survivor 2 are actually the copy spaces. It's where you copy stuff to when you're doing a mark and copy. So typically, objects are allocated in Eden, and then when Eden starts filling up, it triggers a garbage collection event. So it does a sweep through, marks everything that needs to survive, and moves it to one of the survivor spaces. So typically, a GC run in Eden is going to take things in Eden, and then one of the survivor spaces, figure out what's going on, and put them in the other survivor space. So every GC run will result in an empty Eden space and one empty survivor space. That's what happens in the young generation. And if stuff is there for too long, things have to get promoted. And there are two ways that this can happen. The first is simply that you've got some objects in Eden that have moved to Survivor 1, another collection cycle, they move to Survivor 2, back to Survivor 1, back and forth, back and forth. At some point, the garbage collector says, hey, this object has been around for a really long time. It's survived 10 different garbage collection cycles, so I think it's here to stay. I'm going to move it to the old gen so I don't have to think about it very much. And that's the way that you want your objects to get promoted. There's something called a tenuring threshold, which basically tells the JVN how many times you can see the same object in garbage collection cycles before you consider it old. And that's actually an adaptive threshold that they try to make the right decision for you, but you can give it a max limit so it doesn't go crazy. The other way to get promoted to the old gen is quite simply if Eden is so full of stuff that when you're trying to copy it into the survivor space, it doesn't fit. It'll just overflow into old gen because that's where it's got to go. It's got to go somewhere. It's usually a bad sign. It's something that you should definitely be observing and watching out for. It means you haven't sized your JVM and its regions properly. So in terms of performance, again, young generation, always cheap because you're using a mark and copy. It's much more expensive to do garbage collection in old gen, so you want to tune your application accordingly. So let's see some of this stuff in action. Poring over heap dumps and GC logs is useful, but it's often just simply enough to look at a visualization. In this particular graph, we're looking at the GC run rate, so how frequently we're doing garbage collection. This is over a 3-day period. As you can see, during the day, the system is doing more frequent garbage collection and doing less at night because there's less traffic. The blue line down there at the bottom is the CMS run rate, so how frequently is old gen being collected, and it's not very frequent at all. So this is an interesting thing to look at. If you see like a lot of high peaks or thrashing, probably something bad is going on. But this graph is a very healthy system, and your graphs should look something like this in their steady state. And this is a graph of my pause duration. So garbage collection, as we mentioned, tends to have pauses. In this case, you can see that most of the time, it's peaking at about 300 milliseconds, pausing in Neo4j, with occasional spikes up to a second. So it's pretty high, but not terrible, depending on your expectations. A corollary to that is another graph that was pulled from a particularly poor application that is, you can see it's pausing up to 3 minutes. And if you see stuff like that, it's absolutely not healthy. You know, most of the time it's fine in the graph, but every once in a while, too many objects are being put into old gen, and old gen is getting locked up. And cleaning up old gen, as we mentioned, is very, very expensive. So this is my favorite graph that we have. It basically covers memory pool usage. There are 3 different metrics covered here. You have Eden space in light blue, CMS old gen in dark blue, and then survivor space in orange. And this is a 3-day period. You can see that the instance is slightly badly tuned, right? My new gen is almost always full. There's hardly any space. You can see that the old gen is filling up to about 80% and dropping down to about 20%, and that's happening very frequently. This means that there's a lot of stuff frequently being collected in old gen, which shouldn't be the case. Old gen should be the stuff that doesn't need to get collected very often. So why is stuff being promoted to old gen so much? Maybe your tenuring threshold is wrong. Maybe your young gen is too small and things are overflowing into old gen. These are the things that you have to watch out for. So you don't have to remember everything I just told you, do a Google search for the Plumber Java Garbage Collection Handbook, download it, and keep it with you whenever you're on call for Neo4j. I appreciate you sitting through this section. I know it's tedious. Inspecting heap dumps and GC logs is the kind of things that make your eyes bleed. So I'll turn it back over to John, who's going to talk about first the theoretical underpinnings for causal clustering, and then move on to specific operational issues. John?
Thank you. That was thrilling. So real quick, we're going to talk about some of the operational stuff in Neo4j and what's a database without replication. First, though, before we actually talk about Neo4j replication, we've got to talk about Raft. Raft is a simplified form of the Paxos consensus algorithm. This is important because Neo4j uses it in its causal clustering setup. At the simplest level, consensus algorithms allow two different systems or distributed systems to communicate changes to their data in such a way that the client never sees differences between any systems, and you have a high amount of consistency between all members in the cluster. This becomes more complicated by the fact that members of a cluster may fail or a process may become faulty in some way. And so the algorithm must deal with that without allowing a requested change to happen incorrectly. Consensus algorithms are judged to be considered correct at handling failures based on various criteria. Some of these are like termination. Every correct process must eventually come to a conclusion about the requested change. And then agreement, which would be all the correct processes must come to the same conclusion on a single value change. And what that means is that if all the correctly running processes have the same initial value, then all the correct processes must have the same value after applying the same change. And then furthermore, we have things like integrity, which would say something like every correct process decides at most one value change at a time. And this value change must have been requested by some process. In other words, once you put the data in, it shouldn't change unless you want it to. And then, of course, validity, which, assuming all other things are correct, if all processes propose the same initial value, then the initial value must be correct. We talked about correct processes. I said that a lot, but what does that actually mean? There's two types of failures when we talk about processes and computers. And we have like a halting failure and a Byzantine failure. A halting failure is anything that makes the process crash or stop processing input. And a Byzantine failure is pretty much anything else. It could be a network partition or subtle failure in memory or changes to the hardware that allow the underlying state to change. Anywhere the process is still a member of the cluster and is accepting input and sending output, but has in some way had its view of the data or processes corrupted. So these are the type of problems that Raft tries to solve, and how does it actually work? So processes in a Raft cluster may have one of three roles: leader, candidate, or follower. The leaders accept the actual requests, and these are forwarded to its members to achieve a consensus on whether the data change is valid or not. If a data change is considered valid, then the change is committed across the cluster synchronously. And any server, basically any server who is not a master is a follower, and any follower may become a candidate if for some reason the leader is unable to communicate via the internal heartbeats. If a master dies or is pulled from rotation, followers promote themselves to candidates and begin the leader election process. A candidate sends out a message blast to other members of the cluster, and the first server to achieve consensus via majority vote between other members would be elected the new leader. And this happens in the span of a few hundred milliseconds. If no majority can be found, a new election will happen. Usually in Raft clusters, and Neo4j is no different, timeouts on leader election are staggered throughout members of the cluster. What this does is allows you to reduces the chance of ending up in a split brain vote where an equal number of majority members have both elected a new leader separately, and that would be very bad. So these are the two big ideas in Raft: a leader election and consensus replication. And now we can talk a little bit about causal clustering in Neo4j. With 3.1, Neo4j introduced causal clustering. Causal clustering implements Raft as part of its goal to achieve high availability and consistency. Combining this with a disaster recovery plan, such as a standby cluster, gives users a way to meet enterprise requirements for redundancy and uptime. There are two types of servers in a Neo4j causal cluster: core servers and read replicas. Core servers implement the Raft protocol to ensure that writes stay highly available and durable. You should make sure you have an odd number of core servers because that means write consensus is more easily achieved. If write consensus cannot happen for whatever reason, the entire cluster will become read-only to prevent inconsistency of data. Read replicas, the outside circle right there, serve the same purpose in Neo4j as in MySQL, to scale out workloads and remove load from the right servers. It's important to note that rather than using Raft, read replicas use an asynchronous polling mechanism to pull changes of data. With causal clustering, its unique transaction identifiers can be presented by the client so that you don't have to worry about phantom reads or phantom writes. Like you present this unique identifier as part of your transaction, and then you can present that to the whole cluster, and it tells you this read replica has it, so you should read your write from there immediately afterwards. And that's part of the connector. Core servers are added using a discovery process. While this still runs on read replicas, its main job is to form the core. If no core servers are available, the new server will create its own cluster. And if some are available and it can find them through discovery, it'll make itself to be available to be used in the core servers. Once that happens, you have the catch-up process. And the catch-up process says if I have most of the data and I have a little bit of difference, I'll stream the new differences to catch up. Otherwise, it falls back to a full image sync internally. And if that can't be accomplished within enough time, it's actually required that a human comes in and does a manual snapshot of the data in some way and move it over to seed it with enough time so that it can use the catch-up process instead of the full image sync. Earlier, Ryan had talked about how important GC is to the performance of your Neo4j cluster. One of the best strategies for getting consistent performance, you see all these read replicas over here. You actually want to take each one of your workloads and isolate them on a completely different read replica. If you try and shove your BI and your small data critical path stuff all onto the same server, you're going to have a very bad case of the Javas. You want to split those workloads out. Okay, upgrades. Upgrades are straightforward. Just shut everything down and do the upgrade. That's it. I'm not going to go into much more detail. It's a overly complicated 15-step process in the manual, which you can find yourself, but the bottom line is that you have to take massive amounts of downtime to do upgrades, and that's pretty much been a deal breaker for us to move forward at this point. So you kind of have to architect your app to work without Neo4j, which makes it difficult to put in the critical path. If there's a Neo4j person in the crowd, no, we didn't have one, right? So fix that. So in backups, all databases should have a proper and tested backup methodology, and Neo4j is no different. Pretty simple. Backup enabled equals true in your conf file. That's by default. Address, that's not an address to send. That's actually a new listener that it sets up. So like that's going to be like your local address or 0000, and you can specify a port. And this is what you'll connect to with your backup client. The backup client is a tool called Neo4j-admin, and it has a command called backup, and there's a --from, --backup dir. From is the host you're taking the backup from, backup dir is where it's going. You can also do incremental backups, and that's actually really good. You have to specify -- consistency check, and it'll run through, figure out where it is, and then do an incremental, as long as you specified a backup dir with a pre-existing backup. Square, we deal with money, if you didn't know. So security is always top of mind for us. To be completely honest, this is one of the areas we find Neo4j lacking because it doesn't really have much. We'd like to see more focus on intrinsic security in future releases. Otherwise, it comes down to standard best practices. Firewall things off. Don't ever put your database on the internet. Use mutually authenticated SSL, which you have to use S-tunnel for, and encrypt your data at rest wherever possible. Neo4j has no features for that directly, but Java does, and the JVM does as well. And of course, you can always use full disk encryption if that's something you want to do, but I've never had good experiences with that. Fourth, always close deprecated ports and get on a regular upgrade cadence, which means a regular downtime cadence. On the topic of security, our InfoSec team loves using Neo4j to model attack graphs. So what we have is an internal security exercise. We modeled processes, interfaces, IP addresses, hosts, user files, and sockets. And so what we did in this case was we actually took timestamps and made them part of the edges. While the relationships are objects, we can put attributes in them and search them just like nodes. In this way, we model the path of an attack through a network system. We're going to show 4 hosts and a resource they all share called private. You can see that we had one node, Augusta, kind of escalated privileges and created a root process even though it was a non-root user. It then tried to SSH around and eventually got in and began worming its way through the network. That's pretty cool, right? Yeah, I thought so. Moving on, performance. It's pretty much just JVM tuning. It really is. That's like the biggest deal. But all the regular database stuff applies as well. OS memory, you should leave enough memory for your OS file buffer cache to fit the contents of the index and schema directories. And the page cache is used in Neo4j for the data that's actually stored on disk, and you want to make sure that most of that fits into memory. We've heard anecdotally that it works absolutely best when you have 20% more memory than your total data set size, and that's really the only way you're going to end up with perfect performance all the time. So you can sum the store.db files and then just add 20%, and that's a pretty good measurement of how much memory you should have beyond your JVM heap. The transaction logs in Neo4j are kind of like the redo logs in MySQL. The smaller they are, the more you have to rotate them. The more you have to rotate them, the more you don't like yourself. It can also compress and the values in there. We didn't have a good experience with this, but the standard trade-off of IOPS and disk space versus CPU happens. Your mileage may vary. Test benchmark. Stand file system tuning, of course, standard for all databases. Don't ever use CFQ for anything. Use deadline. If you have flash, use no-op. Set no A time and no dur A time or no rel A, but those don't have as much of effect in modern systems. And obviously use modern file systems like XFS. All the standard OS tuning tips that you get with MySQL apply here as well. More for memory, more is better. Always just add more memory. And for CPU, bigger, faster, more, better, everything. Disk, of course, don't put anything less than an SSD. And if you can spend the money for PCI flash, that's even better. And what kind of talk would it be if we didn't talk about monitoring? Neo4j has a couple of ways to expose granular information about your cluster. The first way is setting metrics enabled equals true, which exposes an interface for grabbing these. And the second thing, which is really, really cool, is it supports Graphite natively. So you can simply set graphite.enabled to true, and your Graphite specify your Graphite server with graphite.server, and Neo4j will automatically send metrics to it on a 3-minute interval. And there's further ways you can configure this, like prefixes and interval times as well. You see the manual for more details. I thought that was really cool. And if you actually need to get basic information from the client, from a client access, there's a couple of functions that can help guide your client to the right places. Cluster.role returns the role of the cluster. We talked about Raft, leader, follower, read replica. And if you want to see an overview of everything, cluster.overview. And if your client needs to figure out how to route, like for example, if you set something up, you want to make sure you want to get to a read replica, you just query any instance and say cluster.routing.getServers, and you can add an argument to that to find a specific role and route yourself to the correct place. And currently for us, the main metrics we monitor are number of rolled back transactions, number of open transactions, and total store size. We want rolled back transactions to always be 0. We alert if it goes above 0. And open transactions naturally will just follow the curve of your business cycle. And we've struggled with data store size. We've actually had someone from Neo4j that's very experienced with Neo4j tell us that 30 to 50 gigabytes is ideal for a Neo4j database. We've thrown a couple terabytes in it so far, so it's kind of working out. And that covers what we have, and we're very close on time. Who has questions? Oh man, Ryan?
So you said for upgrades, like you have to shut down and upgrade.
Yeah.
Can you replicate versions of Neo4j or before with the whole cluster?
If you have money, yes.
Okay.
That's the answer for almost everything here. Mostly risk. Our risk applications. So like, we do random stuff. If a customer does an action, there's a chance it'll eventually hit a graph database somewhere to evaluate various things about that action for various reasons.
Oh, mostly Java.
Yeah, it's all Java. Cool. Anything else? All right, I'll give you 3 minutes back. Thank you, everyone.